Hi again, I'm Eric from NTU, and this is the course of Understanding Natural Language Understanding. This is lecture 3. We're going to be talking about past and future of AI. So in lecture 2, we have discussed about some basics of AI, including the fact that it's a big umbrella that includes subsets like deep learning and machine learning. And so we've also talked about supervised versus unsupervised learning in lecture 1. So again, supervised learning happens when you have classes and labels or training data. Unsupervised learning is when you don't have those labels. So things like dimensionality reduction that we talk about, or clustering that we also talk about. But machine learning is a huge discipline that includes other kinds of learning, like reinforcement learning, which is maybe a bit closer to how we humans learn. But what do we really mean when we say learning, machine learning? So the way we learn things as humans actually is very different from how learning happens in machine learning. Also, it's a matter of how, again, we define intelligence. Because, for example, if we take the same approach in teaching someone something, it's a bit like trying to teach someone how to snowboard by just showing them tons of videos of snowboarding. Yeah, you get the gist of what it means to be able to snowboard, but you'll never know how to do that until you try. So let's not forget that even learning is very much multidimensional. And you can see this in many examples in the past. And there was this driving automatic driving car, driverless car that was trained on a lot of training data about mostly pedestrians crossing the road. So the car learned to stop when it saw pedestrians with legs crossing the road, but then it didn't have a robot like this without legs in its training data, and that's why it basically ran over it. So it's important to not fool ourselves when we have these so-called intelligent systems that, as we discussed, are maybe just expert systems that are very much tied to how we model them and the training data that we use. And this is a problem that has happened many times in the past, and we have had a lot of ups and downs in AI, the so-called AI winters, when there was so much expectation in the general public, sometimes even driven by things like science fiction, and then those expectations were not met. So that's why now many people are also talking about a possible AI bubble. So it's true that there have been fails in the past, as we mentioned, self-driving cars running over uh, people, and some robot hotels in Japan that where robots were ultimately replaced back with humans, and ChatGPT hallucinating in court cases, and then, as we mentioned also earlier, some AI companies using AI to screen, to shortlist some CVs, some candidates, and then later on realized that it was a gender bias algorithm. And I don't know if you remember about Ty tweets, the chatbot from Microsoft. The idea was to put out this chatbot out there and being able to learn from the interaction with users and from tweets, but things started going to the wrong direction when Ty from Microsoft started recommending the PlayStation rather than the Xbox to users, and then there was a spiraling down to the point where they had to stop the Thai tweets. It no longer exists. And so why was that happening? Because the algorithm was learning the wrong things. Why? Because it's just a mathematical model, as we discussed, with no common sense, with no true understanding of reality. And so this is also something that we said in the very beginning of lecture one. When we're dealing with numerical data, it's totally fine to use stats and nothing else. But with language, things are different. You need something else. That's why we'll talk about neurosymbolic AI later on. One way to think of this is that, for example, if I ask you which one of these two things that you see here scares you the most, you all probably say the shark. But statistically, you're wrong. You should say the coconut, because statistically, again, uh, coconut kills coconuts kill more people than sharks every year. It's also a problem of transparency, as we has discussed earlier. What's the use of an algorithm that can tell you which patient is going to die sooner if you don't know how and why that prediction was made? So transparency is a very big limitation of AI, of many AI models today, and that's why many of us are looking at XAI, explainable AI. And in a way, today AI is a bit like this guy Nigel, who won the French Scrabble championship, but he doesn't speak French. So this just to say that you don't really need to understand natural language to do a lot of natural language tasks. But that's really the difference between NLU, natural language understanding, and NLP, natural language processing. Also, we don't have to get confused about transformers. They are very powerful and technically advanced tools, as we discussed in lecture 2. But the fact that they achieve human-like accuracy on many NLP tasks doesn't mean that they equal human-like intelligence. So again, they are so much better at representing data than before. But like we discussed before, initially we had to come up with some vectors to represent food items and the weather. And now with embeddings, we can do that much better in a more contextual and semantically meaningful way. But we're still far from representing the true meaning of these things the way that we do. Because when I talk about foods, there's so many things that come to mind: the taste, the smell, the personal experiences that I had, and the personal preferences about these foods. So today, large language models tend to have that kind of veneer of intelligence. We feel like they are as intelligent as us, but they're still very far from representing meaning the same way we do. So let's start from the definition of large language model, because from that definition, we can see what are their limitations. First of all, they are tools to summarize, translate, predict, and generate. So they're mostly optimized for information retrieval. There is no fact checking there. And let's not forget that they're trained to produce human sounding texts. They're trained for plausibility. There is no cognitive architecture behind. It's mostly based on data. And when there's not enough data available to come up with an answer or with an output, then we experience hallucination. And finally, let's not forget that unless we start talking about agentic AI, these are language models. They just answer questions. They don't do things for you. So this is important in the context of AI winters as well, and AI bubble. We need to understand really what AI can do and what it cannot do if we don't want to end up in another AI winter or AI bubble. And this goes back to the discussions that we had in the previous lecture about intelligence. What is really intelligence? So this goes back to the old argument of the Chinese room. The Chinese room argument was about inserting questions in Chinese through this door and getting perfect answers in Chinese. But then inside the room, there is a guy that doesn't know any Chinese is using a rule book. And it just so happened that he nails the accuracy of these answers. So this is a more of a philosophical question of what really is intelligence, or most importantly, what kind of approach we are taking to intelligence. If we take a Machiavellian approach, we don't care what's inside the room. As long as I get a good accuracy, I'm happy. But then if we want to really go back to what the forefathers of AI wanted to do, which was to really emulate intelligence, that's maybe not what we want. And it's not just about hallucination. Gen AI has many other flaws, like, for example, the no syndrome and many other things that for us are common sense, but for these mathematical models are not so much. And this goes back also to some linguistic conjectures about whether it's language that affects the way we think, or it's the opposite, which is thought that affects language. But in any case, let's not forget that language is just a standard. It's just a standard that we came up to communicate with each other. And that's why before we were all connected via the internet, we came up with different languages to communicate. So language in the end is just a standard that is no different from the way different cultures represent distances or weights, for example. And that's also why you have a lot of artificial languages. Sometimes people that came up with their own personal language, or artificial languages like Esperanto, even programming languages can be considered artificial languages. So this is an important point to understand when we're working on text. As we said in lecture one, and mostly we have to convert text into numbers, vectors, embeddings, do some calculation, go back to text. But actually, when we're working with text, we're two steps away from meaning. Text is something that we humans came up with to reproduce some kinds of sound that in prehistorical times we made to start communicating with each other. So we're two steps away from meaning. So it's a mistake to think that text alone can encode and decode meaning the way we do. So this is something that you better understand when you look at other languages that use, for example, characters to emulate specific sound that then translate into meaning. And if you work on social media text or microtext, then this is also clear. Like microtext like this has different meanings in different languages because of the different sounds that they make. In Chinese, five is wu, and many five altogether replicate a sort of crying sound, while in Thai, five is ha, and so many five altogether is ha ha ha, which is basically the opposite emotion. This is very interesting from many different point of view. Some people go as far as saying that we humans evolved so much and our intelligence became so much higher compared to monkeys exactly because of this FOXP2 variation in our DNA that allowed us to reproduce more sounds and then come up with different words, language, and intelligence. So if you need a break, you can watch this funny video that really stresses this point of the relationship between text, sound, and ultimately meaning. So something else that many people like to say is that the way large language models learn language is the same way as we learn language. But that's not very fair, to be honest. Firstly, when we learn a language, we have so many things in common between our own mother tongue and other languages. So to be fair, we need to choose maybe a language that doesn't have any common phonemes, because a large language model doesn't have the luxury of already knowing another language. So maybe a language like German that is very different from other languages in Europe, but that's still not fair. So because we still have a common alphabet in many cases. So what if we change to a completely different structure where we have characters or even Cyrillic to represent language? Would then be a fair comparison? Still not, because we still, in many languages, we have that common structure where we have subject, verb, and object. So if we take another language, maybe a tribal language, it is completely different in terms of phoneme, alphabet, and structure. Is it still a fair comparison? Actually, it's still not, because no matter what kind of structure and alphabet we use, we're still using the same common sense related to the objects and meanings that we want to represent. So the only fair comparison would be trying to learn an alien language where we really have no commonalities between the two languages. So this is an important point to make. Sometimes in computer science, we like to make these sort of metaphors or analogies that sound very cool, but actually they can be somewhat misleading sometimes. So like saying that deep learning is the same as the way we learn things actually is very wrong, because we don't learn things the same way. Yeah, maybe we learn a lot of things by example, but then there's also a lot of learning that goes through common sense, experimenting, or even top-down learning, like our parents telling us how things work, what to do and not what not to do. And similar with neural networks, that, yeah, they resemble very much the structure of synapses in our brain, but the synapses in our brain do not work like a neural network. So let's not forget that. Although we have these nice analogies in computer science, that's not exactly how things work. So in our team, we also look at these kind of problems like human cognition versus AI cognition. And one interesting thing that we discovered recently is that the reasoning that we use to answer questions versus, for example, ChatGPT is very different. When we answer questions, we tend to leverage a lot our own personal experiences and very concrete concepts, while ChatGPT tends to gravitate more around abstract concepts. So the truth is that we're still very far from emulating even just the structure of the brain. In fact, the total number of neurons in the brain falls in the same ballpark of the number of galaxies in the observable universe. So we're very far from even just emulating the neuroplasticity of the brain. And it's not just about that, it's also about the efficiency of the brain. So AI efficiency is also something that it's very important. Sometimes we need rooms full of servers that consume a lot of electricity and water for cooling, while the brain can do all the amazing things that we can do in a very limited space and consuming very little energy. So as we mentioned, when we talk about AI recently, the discussion is also a lot about AGI, artificial general intelligence, to step beyond just expert systems. Some say that it's coming very soon, some say that it's impossible. Personally, I think that once again, it depends on how we define intelligence. So definitely we can see ChatGPT and the likes of it to become more and more intelligent in the years to come, but it will be just one kind of intelligence. And no matter how smart they become, they will never truly know the meaning of things like pain and pleasure or really feel emotions. But then on the other hand, you have people like the late Marvin Minsky that said that we actually know different from machines, in a sense that our bodies actually do a lot of things unconsciously without us having full control on our bodies. mostly pre-programmed by biological evolution, if you wish. So we humans are just very complex machines, according to Marvin Minsky. And then there are others that go as far as saying that the goal of humanity actually is simply to create an AI that can go and live beyond us, free from our biological limits, and go and colonize the universe and live much longer than we will. So these are all, of course, philosophical conjectures, and there may be questions for the future. But now it's important to start asking the right questions to engineer the future of AI. And some of these questions are whether we ourselves, we humans, are a good model or not. And this sounds like a trivial question, but actually it's not, because in many cases when we invented things, as humanities, we took inspiration from nature, but not every time. For example, planes don't flap their wings. So the question here is, should we come up with a different kind of intelligence that is not like human intelligence? When we talk about affective computing and emotions like we did, there's also a big question on whether we should emulate the full spectrum of emotions in a machine to make it truly intelligent, or maybe conveniently leave out negative emotions. But this is also an open debate, because then you have negative emotions, for example, like frustration, that sometimes are good for even a machine to stop doing what they're doing and change perspective, change task. Is it fair for us to, is it okay for us to feel emotions for machines? So this is also something that has been discussed in some movies and also in some news recently. And then there are long debates that go on from the 70s about how embodied AI should look like. Should they look more like us, or should they look like completely different? The famous uncanny valley problem. And then something that is more popular in the EU right now is whether we should put a cap on how intelligent an intelligent system should be, and many more questions, some again very philosophical, like how fair is it to create an intelligence and then keep it trapped in a server or in a computer or even in your phone? So again, it's an open debate, and different AI professors have different opinions, some very extreme, like again, Geoffrey Hinton recently saying that AI is very dangerous and we should be aware of the negative consequences that it can have, like a AI apocalypse coming soon. And same going in the business world, as you know, Elon Musk and Mark Zuckerberg having different opinions about the benefits and the dangers of AI. So personally, I don't believe in an AI apocalypse coming anytime soon, because ultimately AI is just a very powerful tool. And so it depends who is using it and how it's being used. So it's not different from other things that we experienced in the past, like genetics or the atom. But the real risk is that we may create an AI with a specific goal in mind, which could have unexpected consequences, like we unexpectedly kill insects when we are building some sort of structure. These are also known as the paperclip scenarios that Nick Bostrom came up with for the first time. And so this can really be the real risk. But and some people may think, okay, but how likely is this really to happen, right? And the truth is that it already happened many times in the history of humanity. One good example is plastics, that were a great invention about a century ago, but they are now threatening our own existence. Or even social media. Social media algorithm is very good today in a sense that it achieved the goal or keeping us glued to our devices. But then the question is this really the future that we want, where people are increasingly technology dependent and not really talking to each other anymore. So with all this in mind, we came up with this sort of research manifesto, which is really a call for collaboration for anybody working on AI who is interested in these topics. So the first pillar is definitely multidisciplinarity. AI is no longer a computer science discipline only. It's also about psychology, sociology, ethics, and arts, and much more. Secondly, an important pillar that we'll discuss more in the next lecture is task decomposition. Now there is this tendency to just throw as much data in a model and expect this to magically be able to handle all the subtasks that are required for natural language understanding. But sometimes it's better to have a more modular approach, like we'll see in the next lecture, or in cases like here, our AI scientists, where it's using purely statistical models, like large language models, but it's not using just one model, it's using a lot of them that are interfacing with each other to have a better understanding of the next task. Parallel analogy is also a concept introduced by the late Marvin Minsky a long time ago, and we've kind of forgotten about it. So as engineers, it's very easy for us to focus on achieving the best kind of representation, the best kind of model, but sometimes it's better to have maybe the same data represented redundantly in different formats so that I can switch to a different format when problem solving starts to fail. This is a bit like we humans do when we can't solve a problem and we try to look at it from a different point of view. Symbol grounding is the central pillar, and it's really one of the main problems of AI today. As we mentioned, we have these embeddings that represent words, but then there is no really any grounding of the meaning that these symbols represent in the AI model. So we'll talk a bit more about this in the next lecture. We've also talked a lot about similarity metrics earlier, like cosine similarity and Euclidean distance. And the problem with these kinds of distances is that they are not topology aware. So for example, from a Euclidean point of view, you can have the two data points in a multidimensional vector space are very near to each other, so supposedly very similar. But then if these two belong to different manifolds, they can actually be very different. That's why cosine similarity sometimes doesn't work, like as reported by Netflix in 2024. And ultimately, it's also a question of what kind of similarity we are really calculating there. Because, for example, if you take two concepts like happiness and sadness, from a semantic point of view, they are very similar because they're both emotions. But from an affective point of view, they are polar opposites. Another important pillar is intention awareness. So when we communicate with each other, we have a model of the person that we're talking to. So the way we communicate is different depending on the person that we're talking to. So this is very much tied to concepts like theory of mind and even personalization. And last but not least, we have trustworthiness. How do we define trust between AI and humans? So at the very least, we should have transparent systems that tell us how they came up with the specific classification or item. So in this short paper, we look at recommender systems. And the question is, many of the recommender systems that we use, like Netflix and Amazon, and even dating apps, who tells me that the next item that I get recommended is really what's best for me and not what's best for the business model of the company? So again, at the very least, we should have transparency. We keep going back to the concept of transparency. So that is it for this lecture. I hope that was some food for thought. If you have any questions or even comments, don't hesitate to ask me, and I'll see you at the next lecture. Ciao.